Now we'll have Ksenia Shakhgildyan from Bocconi. And it's second to last. We'll have yet another one. And yeah, it's perfect. So go for it, Ksenia.
Hello, everyone. Do you hear me well? Do you see the screen well? Sounds good. Hello, everyone. Thank you very much for joining. I am Ksenia Shakhgildyan. I'm a postdoc at Bocconi University, and today I'm going to talk about the main chapter of my PhD dissertation at UCLA on non-parametric identification and estimation of contests with uncertainty and its application to the U.S. House of Elections. To start with, what is a contest? A contest is a natural model of costly competition, as it describes situations when all players spend resources, for example, exert efforts, spend money or time, in order to affect their probability of getting an object or a prize. Importantly, the effort is a sunk cost, since no matter whether a player wins or loses, the cost is always incurred. A broad variety of real-world situations fall under this description. Here are just a few examples. In electoral competition, all candidates raise and spend money for their campaigns, but only one candidate wins the election and obtains the seat. The effort in this case is represented by campaign expenditures. In research and development, firms incur huge R&D expenses, but only one gets the patent. Other examples would include lobbying, sport events, arm races, and so on. Today, I will focus on elections in my application, but my model could be applied to all of these settings. All these real-world situations are inherently uncertain, meaning that player who exerts the highest effort can still lose. For example, the candidate with the highest campaign spending can still lose the election. The company spending the most on R&D can still not get the patent. To be able to account for this uncertainty and estimate it without putting many restrictions on the model is particularly important. The econometrics of this problem, however, is complicated and not well developed. And in my paper, this is the issue I address. More formally, the main object that determines the contest environment is the contest success function, which maps the efforts of the players, BIs, into the probability of winning, PI. As an example, in an OP auction, there is no uncertainty given the efforts, since the player which exerts the highest effort always wins. In Taleb contest, the probability of winning is determined by the relative efforts of the players, so uncertainty takes a very particular form. Instead, in this paper, I account for uncertainty in a much more flexible way. The contest success function in my model is determined not only by the efforts of the players, but also by nonparametric stochastic components, epsilon i's, that summarize other factors that could influence the winning probability apart from the efforts. I denote the ratio of epsilons xi and call it uncertainty. Depending on uncertainty xi, players' efforts have different effects on the winning probability. Importantly, this model generalizes many common contests. In particular, OP auction is a special case when epsilons are equal to each other. Taleb contest is also a special case when epsilons are independent and have exponential distribution. Moreover, such contests as logit form and many others are also generalized. Instead of imposing any type of parametric assumption, I will non-parametrically estimate the distribution HXI of uncertainty. It will determine the asymmetry in contest success function between the players. I examined the model with two asymmetric players, which in my application would be an incumbent and a challenger. Those two players have different cost types CIs distributed according to FI, and in application, these types determine how costly is it to raise campaign financing for each of the candidates. I consider the game of incomplete information, meaning that each of the player's types is his private information, not observed by the other player, but the distributions of the types are common knowledge. Moreover, players know only the distribution of uncertainty, not its realization. To make it more concrete, in this model, the expected payoff of player 1 when he exerts the effort B1 is given by the difference between the expected probability of winning and the cost of effort multiplied by the effort itself. I studied the following research questions. First, from the theoretical perspective, I answer to the question of how to identify and estimate both the distribution of uncertainty as well as the distributions of the player's cost types, FIs, from observed efforts and win outcomes. I also show that estimators are consistent and asymptotically normal. Next, I apply the model to the Yes House of Representatives elections and answer the question of how to separately identify two sources of incumbency advantage. The first comes from the asymmetry in private costs, since incumbent might have better ability in raising money for the campaign than the challenger. And second, even if the incumbent and challenger spend the same amounts in their campaigns, the incumbent might have higher chances of winning due to better reputation, name recognition, and other possible non-monetary factors. This separate identification is particularly important for policy counterfactual analysis, since only campaign financing can be regulated by the authority. I find that imposing a limit on expenditures is more effective than public campaign financing of the challenger at reducing the incumbency advantage. Now I will briefly summarize the theoretical results. I consider the strictly monotonic Bayesian equilibrium of this incomplete information contest. I prove existence and I derive the first order conditions of this model. And then I prove a novel two-step and propose a novel two-step identification procedure. So first, I would identify the distribution of uncertainty HXI using the information on win outcomes and efforts. And second, I would identify the distribution of the player's cost types using the distribution of uncertainty found in the first step and the efforts distributions. To estimate the model, I propose kernel-based plugin estimators of both the density and the uncertainty of the player's cost types. And then I prove consistency and asymptotic normality of these estimators. I also derive the asymptotic distributions using Fréchet derivatives. Now I would like to discuss the application results. The US House of Representatives elections happen every 2 years. Currently, there are 435 voting seats, and the winners serve 2-year terms. I consider around 6,500 incumbent challenger elections from 1972 to 2016. On average, incumbents spend a lot more, about 2.5 times as much as the challengers on their campaigns. And what is especially striking is that incumbents won in 94% of the elections. Using my theoretical model, I quantify two sources of incumbency advantage. The first is due to asymmetry in cost of success function. Even in the case when the expenditures of incumbent and challenger are the same, incumbent would win in 85% of the elections. Possible explanation is that the incumbent is generally more popular, has better reputation. And the second advantage is due to asymmetry in cost types distributions. Challenger's distribution first order stochastically dominates the incumbent's one, which means that it is more costly for the challenger to raise money than that is for the incumbent.
About 2 minutes.
Thank you. And now let me describe the counterfactual analysis very briefly. So I considered two policies, public campaign financing of the challenger and imposing a limit on candidates' expenditures. So first, consider the public financing of the challengers such that the resulting cost type distributions of incumbent and challenger are equalized. In that case, the incumbent's winning probability decreases by approximately 4 percentage points. At the same time, the reform would lead to the increase in expenditures of both candidates due to game theoretical nature of the model. But in contrast, the limit on expenditure such that both candidates spend the same amounts leads to a bigger, almost 9 percentage point decrease in incumbent's winning probability and lower total expenditures of incumbent and the challenger. That means that the limit on expenditures is more effective than public financing in terms of both lowering the incumbent's advantage and total campaign spending. To conclude, in this paper, I non-parametrically identified and estimated the incomplete information contest model with uncertainty. I recovered the distributions of costs as well as the contest success function from the efforts distributions and win outcomes. I have also applied the model to the US House of Representatives elections and estimated two types of incumbency advantage. The counterfactual analysis shows that the limit on expenditure outperforms public financing of the challenger in terms of reducing incumbency advantage. Thank you very much for listening, and please let me know if you have any questions or comments.